Hello, my name is Philipp Fent and I'm from the databases group at the Technical University of Munich. Today I'm going to present our practical approach to group joins and nested aggregates. So first, group joins are an operator that combines a join with a group by and avoids building a duplicate hash table that would be on the same key. So here in this case, it is possible to do a group join because we have the same attribute over which we group by and join. And for our approach, we also only looked at key foreign key joins, so the left-hand side is duplicate free. The traditional approach that many papers previously discussed is to build a big combined hash table that stores keys and aggregates directly in place. However, this is not a great fit for modern hardware because with multiple threads, updating these aggregates here in place causes a lot of contention. So when updating these aggregates from different threads, we actually fight for cache lines or locks here that guard these aggregates, which is something that we want to avoid. What we can do is we can reuse a tactic from regular group by operations where we first build a thread local group by pre-aggregations and only merge them later on into one global hash table. And we can do this as an eager write execution for our group join as well, where we just reuse the thread local logic of a group by operator. So here we group this as efficiently thread locally and merge it into a big global hash table, and then probe with the left-hand side. And since we know that the left-hand side is duplicate free in a key foreign key join, we can directly continue on with the next operator and keep the values that we have here in registers. This works very well if every tuple from the right-hand side finds a join partner in this join part of the group join here. However, this does a lot of wasted work when the group join is not very selective for the is very selective for the right hand side. So if not every group from the right hand side finds a join partner, and we do a lot of wasted work. To avoid wasting work, we propose another implementation that is a memoizing group join. So we go back to the idea of building a global hash table, but in addition, we keep thread local hash tables to aggregate heavy hitters. So here in this case, in the global hash table, we add another thread marker that marks the thread this aggregate belongs to, and we update this thread ID here with the first thread that initializes and updates the aggregate. So in the common case, each aggregate is only ever touched by exactly one thread, which means that we can directly update them in place and never get even in the situation that would have caused contention. But we still want to defend against the case where we actually have contention, for example, heavy hitters that are present on every thread. So when we have a heavy hitter, so in this example here for the third aggregate, which is then also present on thread 1 and 2, thread 1 and 2 would then probe our global hash table, see that it is already owned by thread 3, and then remember this pointer in a thread local hash table and store a thread local aggregate in a local hash table. And later on, we can reuse this memoized pointer to just follow this pointer to update the global hash table in place without going through the global dictionary again. So to compare this, we evaluated the used memory here, and this shows very nicely how the different operators and implementations play together. So for a separate execution with a separate group and with a separate join and a group by, we first built the join hash table up front in about 500 megabytes of memory, and later on, when we probe through that join, we build a group by hash table that aggregates all the groups, which is another 1 gigabyte of memory. So we get a memory usage of about 1.5 gigabytes. In the memoizing case, we build a much larger hash table up front, which also stores the aggregates in place and only uses about 1 gigabyte of memory. And then in the probe phase, we directly update all the aggregates in place without the need of allocating very much dynamic memory, which is nice for execution, and heavy hitters occur very infrequently anyways, so this makes a lot of sense in this case. Eagerly aggregating, on the other hand, is here the most efficient approach, because in this setup, each tuple from left and right hand side finds a join partner, so eager aggregation can pipeline through and be a lot more efficient without the need to defend or doing unnecessary work. But this is certainly not the case in any case. When we put group joins into practical use, where we most often use group joins is to decorrelate nested aggregates in subqueries. So here, group join makes semantically very much sense. However, these nested subqueries often have a having predicate that will in turn influence the join orderings and the most optimal join plan that is afterwards this subquery. For example, when we look at TPC-H query 18, here we have a nested aggregate, and this nested aggregate is filtered by a having predicate, and depending if this having predicate is selective or unselective, this influences the selectivity of the semi-join afterwards, and in turn generates very different optimal operator plans, and this makes a very noticeable difference. So we definitely want to estimate aggregates, and as a first baseline, we can approximate numerical columns as roughly normally distributed. This is very cheap to estimate, and it generalizes nicely, but this has the unfortunate downside that it is symmetric, and a reality of datasets is that they are skewed. When we look at real-world datasets, for example, the IMDb movie rating, a skew normal fit, what we then actually use, is a much better fit because it has a heavy long tail to one side, but still follows roughly a normal distribution. For TPC-H, which is just uniformly randomly generated, we get a much worse fit. However, the CDF is still roughly approximated, so it is good enough for at least a rough join estimation. So to put the skew normal distribution into use, we use the CDF function to estimate if a constant or a predicate is lower or equal than our column. And we can also combine different define algebraic operations like binary operations like plus or minus on these distributions, and we can also approximate aggregation functions. So when we have input data in a base column X here and a group size, which we estimate using a hyperlog sketch, then we can combine these two to build the sum using a multiplication operation. And min and max actually follow an extreme value distribution, but this is also something that we can approximate using a skew normal distribution. So to summarize, the overall impact of our group joins and nested aggregates can be very big when we correctly advise a good group join. For example, we see here in TPC-H query 13 that we have a big impact because we advised a good group join and a good group join implementation that speeds up the whole query. However, when we look at bigger queries like in TPC-DS, group joins only make out about 1/8 of all of the operators that we have in these queries, so their overall impact is limited. We also see that having estimates can have an impact on a number of query plans, but their impact is also very limited because the join orderings aren't affected as much, and we even get one slightly slower query with TPC-DS query 73. However, this is not a big problem because we actually discovered this case here, and we already fixed it, and we are now better in any case. And improving these estimates even let us uncover another bug. So we move in the right direction.